Hello, my name is Wahid and I'll be implementing a neural ODE-based finite viscoelasticity model in FEM for my project. Here's an outline of my talk. I'll go over motivation behind the study, problem setup, methods, results, and I'll summarize my talk. So, first things first, motivation. A lot of materials show viscoelastic behaviors, such as polymers, metals, and soft biological materials like skin. And there are three different classes of viscoelasticity theories: linear viscoelasticity, finite linear viscoelasticity, and finite viscoelasticity. And among these, finite viscoelasticity is the most unconstrained, free form of viscoelasticity, which I'm trying to adopt in this project. And I'm trying to do that in a data-driven way because most of the viscoelasticity theories that we're using today, they're decades old and they lack seriously in terms of flexibility. But data-driven methods have proven to solve this problem. In particular, I'm using a new class of neural networks known as neural ODEs to achieve this, and these allow us to have flexible models that adhere to some physical constraints such as the second law of thermodynamics. So, in summary, I want to implement that in a 2D plane stress FE solver in Python, and I want to simulate this square patch of skin as shown on the right. I will load this, wait, and then unload to observe how viscoelasticity affects the behavior. The strong form of the solution, the problem in this study is given as this: to find the displacement field U such that this equation is satisfied for all positive t's, subjected to these boundary conditions, where gamma is the surface of the body. And in weak form, this turns into this equation where tau EQ and tau NEQ are the Kirchhoff stress of the equilibrium and non-equilibrium parts of the deformation. And tau NEQ is given in terms of an evolution equation, which is a function of the left Cauchy-Green deformation tensor B. So it's in spatial coordinates, which will become important later on. Okay, going into methods, if we linearize that weak form of the problem, we get this equation here, where this expression inside the parentheses is the blackboard C, or material tangent, and now the problem is how to obtain that. If we take that entire parentheses and simplify it, we'll see that at the end we get a push forward operation of this capital C to get small cc. This is the final form of the linearization of the weak form, where we have the small cc, which is a push forward of this large cc, which is in turn composed of two parts, CEQ and CNEQ. The CEQ part is easy because it's the same as hyperelasticity. It doesn't depend on the evolution equation, but CNEQ is a little bit difficult because, as I said, my evolution equation is given in terms of in spatial coordinates. And to solve this problem, I've been following two different approaches. In approach one, what I do is, in summary, without going into too much detail, I try to use a trick here where the deformation gradient is given in terms of the inelastic part of deformation gradient from the previous time step, which is a constant in the current time step. And if you follow with this derivation, at the end you will see that the derivative of SNEQ with respect to C, which is CC NEQ, it's given in terms of this C tilde, which is a fictitious tangent. And I was trying to see if I can obtain this guy with a numerical approach, but so far that hasn't been working out. And then approach two is as such. So I currently have this function that gives me the spatial stress, or tau, given the deformation gradient, given the left Cauchy-Green deformation tensor. But it does so by spectral decomposition of B into lambda and the eigenvectors. Now, B and C, the reference equivalent of B, they share the same lambda, but their eigenvectors are different. I can make use of this by having a constant f while calculating the material tangent, but where c will vary. So what I'll do is I will obtain lambda and capital N's, which are the eigenvalues and eigenvectors of C. And then I can use this f, which contains some error, to transform that capital N to the small n as I had before. And also at the end, I'll use this erroneous f to go from tau to s with a pullback operation. Now, this is not an ideal situation because obviously this introduces some error because I'm keeping f fixed and only varying c when calculating the tangent. But I'm hoping that this error is small enough for me to obtain some convergence. However, unfortunately, so far I haven't had any success with this. I don't have much to show in terms of results, so I'll just show some slides from my code. This is the same thing that we had in class. The only difference is my stress is obtained in terms of this eval RG, which is the evolution equation. And this is at eval RG. It takes f, it calculates b from that f, and then it follows through with the evolution equation to get tau in a q, and from that it gets sigma and returns the sigma. So for the elastic moduli, I have this eval cc function, I call that, which gives me the capital C, and then I push it forward to get the small cc and turn it into Voigt form. And this is what this eval cc function looks like. So once it gets the 2D, keep in mind that we're working in 2D Python, but the evolution equation requires 3D tensors. So this function gets C2D and F2D. But we need to find the tree components of those. One very naive approach would be to take the determinant of these and use that for C33 and F33, but that wouldn't work. So I wrote another function that solves for C33 and F33 using Newton-Raphson, and that gives us the 3D stress, the 3D C and F. And then I vary every component of the C bit by bit to get the numerical tangent, or the STC. Here, as you can see, I have this new modified form of the eval RG function, which is in reference coordinates, and this is how that works. So it takes C and F, which is where C is varied a little bit, but F is constant for the entire duration of this. That C is decomposed into lambda E and capital NA, and then I use this F that contains some error and I do that RU decomposition of F to get R, and I multiply R with capital NA to get small na. Unfortunately, though, this hasn't been working out so far. The scheme diverges somewhere and I get nonce in most cases. In some other cases I do get the small cc, the capital CC, but it hasn't been a reliable approach. So in summary, I'm trying to implement a neural-ODE based model of finite viscoelasticity in FEM. Finite viscoelasticity is important because it allows for unrestricted simulations, which are really important in things like simulated surgery, where we need large deformations and large deviations from thermodynamic equilibrium. Solving the weak form of the problem in FE requires knowledge of the material tangent, which is the derivative of S with respect to C. But my evolution equation is given in spatial coordinates, which takes B and gives me tau. And it's proving difficult to get the relation C to S. If you have any suggestions, please let me know. Otherwise, hopefully I'll be able to figure out a way until the deadline of the project. But this is the summary so far. Thank you for listening to my presentation, and let me know if you have any questions.